Hello everyone and welcome back to Thermo Shorts, where we're breaking down the big ideas in the large lectures so you can get a glimpse of the main points that we're talking about here in thermodynamics for mechanical engineers. So we've been talking about closed systems and the first law for closed systems in an elapsed time format. Now, this lecture is really about how we're going to find that change in energy, the change in internal energy specifically, and it comes down to this first question. We need to know what's in the system that we're looking at. So we talked about last class how generally we'll use this first law is to use the expression for work, the integral of PDV, to find W, and then we'll fix states to find specific internal energies at state 2 and state 1, and that will help us find the change in internal energy, which is the change in the total energy if we can neglect kinetic energy, potential energy, and spring energy. And then we use the first law to solve for the heat transfer either into or out of the system. But how do we find specific internal energy? Like I said, it depends on what's in our system. Generally in thermodynamics, at least for mechanical engineers, the two types of things we're worried about inside the system are either water or air. So for the examples we'll talk about today, we'll think about water in our system. Now, the thing about mechanical engineers is if you give us heat, usually we're going to want to boil water, or at least that's something that historically we've been very interested in doing, because as we boil water, water turns into steam, so it expands, and if it expands over fan blades that are in, say, a turbine connected to a shaft, we can turn that expansion into mechanical work in the form of a rotating shaft. So what's in the system? This is always a two-part question, right? So generally, is it water, or is it air, or some other ideal gas? And here we've chosen water. Now, when we've chosen water, we want to know, is it a liquid, a vapor, or some combination of the two? So we have this vapor dome. Here, this is a graph of temperature versus specific volume. And if we're over here above the vapor dome and to the left, we have liquid water. In your textbook, you'll find tables for liquid water in table A5. If we're above the vapor dome and to the right, you'll have superheated water vapor or steam. You'll find tables for this in table A4. Now, you could also have some equilibrium condition if you're under the vapor dome where saturated liquid water and saturated water vapor, so that's liquid water or water vapor at the temperature required for boiling, these things can exist at equilibrium if you're under the vapor dome. In a case like this, we'll want to look in the textbook for table A2 or A3, depending on whether we know the temperature or the pressure. So how does this work? Here's a quick example that we went over in class. We're asked to find the properties of water, here the specific volume, the specific internal energy, the specific enthalpy, which we don't really know much about yet, and the specific entropy, which we also don't really know much about yet. We're asked to find this for water that's at 10 megapascals and 400 degrees Celsius. So what do? Right? So I know what's in my system is water, but now I want to know what's the phase. Is it liquid? Is it vapor? Or is it a combination of the two? So usually if I don't know what the phase is, I'll assume first, or maybe I'll check first, whether or not we're under the vapor dome. So I'll look for either table A2 or A3. In this case, I'm going to check the pressure. And then table A2 or A3, whichever one I look at, will tell me what the boiling temperature at that pressure is. So in this case, I've looked on table A3 because I want to find the pressure first. So A3 has pressures in nice round numbers and tells us the temperature water boils at that pressure. If I looked on table A2, these two columns would be reversed. I'd have nice round temperatures, and then it would tell me the pressure where water is boiling at that temperature. So in this case, we're talking about 10 megapascals. but the pressure here is given in bar. So I need to remember that to convert from bar to megapascals, I have to multiply by 10. So 100 bar is equal to 10 megapascals. Here, what I see is that if I had water at 100 bar, then the boiling temperature is 311 degrees Celsius. So here, we're talking about water at 400 degrees Celsius, which means it's past this boiling temperature already, which must mean that it's a superheated vapor. So now, on my vapor dome diagram up here, I need to be up in this superheated water vapor region, which means I'm going to look at table A4. So table A4 has lots of subtables that look like this, and they're all grouped by pressure. So the first thing I need to do is find the right subtable that has 10 megapascals or 100 bar. So I look here at the header in the table, and I find that this is the right subtable. Now I'm going to look for the row here. So these are properties at different temperatures. And now I'm going to look for the row that's 400 degrees. Now here I'm fortunate because there is a row that's actually 400 degrees. Because this is exactly a row on my table, it's not too difficult to get these properties that I'm looking for. I just pick them off, making sure that I get the correct units. Those units are all in the header here in the table. So it's not that hard if I have the right row on my table for the temperature I'm looking at. But what happens if I'm in between rows? Like let's say I had 494 degrees Celsius. How would I find the properties? The answer here is we have to do linear interpolation. So this will be the focus of the next class, but basically if we have a linear relationship, in this case between something like temperature and specific internal energy, that means if I have 2 points on a line and I've moved some percentage of the distance in temperature, then I'll also have to move that same percentage between my 2 points for specific internal energy. Now, there's lots of different ways to do linear interpolation. The way that I like to do it is to define this interpolation factor A, which tells me the per unit or percentage, if you multiplied it by 100, distance I've traveled in temperature, and then has to equate that to the same per unit difference that I've traveled in specific internal energy. But like I said, that will be the focus of the next lecture. So thanks for joining me on Thermo Shorts. I'll see you next time.